All right, so the first problem says an elevator filled with passengers has a mass of 1700 kgs. The elevator accelerates upward from a rest at a rate of 1.2 meters per second square for 1.5 seconds. So it starts from rest and accelerates at that rate for that time. Calculate the tension supporting the cable. All right, so here's the elevator. It has a mass, the tension in the cable, and there's the weight, and that the elevator is accelerating upward at 1.2 meters per second square. So if you take this direction to be positive for the y-axis, T minus mg, the forces in that direction, T minus mg, should equal m times a. Okay. So we'll be using Newton's second law. Net force is equal to the mass times acceleration. So the tension is mg plus ma. Okay, so you see when the elevator accelerates upwards, the tension in the cable is greater than the weight. Okay, so if the cable breaks, that's when it would break. Okay, when the elevator is accelerating upward. Okay, now you can have an acceleration upward in two cases. You're starting from rest and speeding up upwards. When is the other case where you would have an acceleration upward like that? Very good. So if you're coming down and you're slowing down, your acceleration wouldn't be upwards. Okay. So that's when the tension is greatest. Okay. And so I will do it like this. mg A is 1.2 meters per second square. And I will write it like so. So so this is there's 1g and this is 0.212 g's. So this is 1.12 mg. So the tension in the cable is 12%, 112% of the weight of the elevator. Okay? Then part B says the elevator continues upward at a constant velocity of 8.5 seconds. What is the tension in the cable during this time? Okay. So when the elevator is moving at constant velocity, the tension is equal to the weight. So whenever the elevator is moving at constant velocity, the tension is just equal to that. Yeah. The elevator decelerates so the elevator started off at rest, it accelerated, then it moved with constant velocity, and then it's getting ready to stop, so it's decelerating. Okay, so when it's decelerating, the acceleration is in that direction. Okay. So the elevator decelerates at 0.6 meters per second square for 3 seconds. Now the acceleration is pointing in this direction. And this is 0.6 meters per second square. Okay. And so, well, So we'll choose this direction as positive. Mg minus tension will equal m times a. Okay. We'll bring this over on that side, this over on this side. So tension is equal to mg minus ma. Okay. And so this works out to 0.94 mg. So when the acceleration is downwards, the tension is 94% the weight of the object. Okay. You see, so when it's accelerating at with an acceleration pointed downwards, the tension is less by that amount. You see, this thing can be zero if A were equal to G. So if the elevator were free falling, then the tension would be G, would be zero. Okay. All right, so the tension was 1.12 mg when it was accelerating upward. When it was moving at constant velocity, it was mg, and 0.94 mg when it's accelerating, the acceleration is downward. How high has the elevator moved above its original starting point? Okay. What is its velocity? So part D, here the elevator starting at rest. And so how long does it accelerate? 1.5 seconds. This is where it is at 1.5 seconds. And then it's going at constant velocity for 8.5 seconds. So that is 9-10 seconds. It's right there. And then it decelerates, okay, and stops at 13 seconds. So let's calculate the velocity here. Velocity here would be v naught. Okay, so I'll do all these. Velocity at 1.5 seconds is v naught plus a times t, 0 plus 1.2 times 1.5 equal to 1.8 meters per second. So here it's going at 1.8 meters per second. And then it goes at 1.8 meters per second. It's going at constant velocity for the next 8.5 seconds. And then let's calculate the velocity here. So velocity at, what is the velocity at 13 seconds? So we can apply these formulas. When can we apply these formulas? When the acceleration is constant. So in this leg, the acceleration is constant. Okay, so that's a 3-second journey. And the initial velocity at this point, what is the initial velocity at this point? Very good. Okay. So this is, so we're calculating at 13 seconds, but so we'll have to write it as 3 seconds. So I won't write that. So initial velocity is 1.8 meters per second. And the acceleration is in the opposite direction, and it's 0.6 meters per second squared. And so it does come to rest. So what we have done is it started here when it after 1.85 seconds, 1.5 seconds it was going at 1.8 meters per second, and then it came to rest at that point. Now what we want to do is calculate all these distances. So we'll calculate this distance while it's accelerating, then we'll calculate this distance while it's moving at constant velocity, and then calculate this distance again while it's accelerating. Okay. We'll call this D1, D2, and D3. Okay. All right, so D1 x minus x naught equal to so this is D1. The initial velocity was 0 for that leg of the journey. Acceleration was 1.2 meters per second square. And the time was 1.5 seconds. So 1.35 meters. So roughly just 4.5 feet. So the elevator accelerates roughly your height, okay, for that amount of time. And then we'll do D2. That's again x minus x naught equal to v naught t plus 1/2 at squared. The acceleration was 0 for that leg of the journey. What was the initial velocity? Yeah, there you go. So D2 equal to 1.8 meters per second, and this is 8.5 seconds. So that's where most of the distance is covered. So 15.3 meters. Okay. And then the last leg of the journey. So x minus x naught equal to v naught t plus 1/2 at squared. So now we're looking at this leg of the journey. This is D3. What is v naught here? 1.8 meters per second. And that journey lasted 3 seconds. What was the acceleration? Mm-hmm. Okay. Okay. So the total distance traveled was 1.35 plus 15.3 plus 2.7. Okay, that's 17, 18, 19.35 meters. Okay. So roughly 5 meters is a floor. So you climb 4 floors. So some of you guys might have things hanging from your rear view mirror in your cars, and those can be accelerometers. Yeah. So you could do an experiment. Your phones have an accelerometer as well. Okay. You'll see. So if your car is going at constant velocity, anything hanging from the roof will be hanging vertically down. Okay. Now, if you accelerate, then this object hanging will be at an angle like that. Okay. And the greater your acceleration, larger this angle. For infinite acceleration, this will be hanging at 90 degrees. Okay. And of course, when you're braking and the acceleration is that way, then this will hang that way. All right. So now let's relate this acceleration to this angle. Okay. Well, why is it hanging that way? Here's why. So here's this mass, there's the tension. If it's accelerating like that, is that thing? Okay, so 2-gram ball hangs from a roof of a freight car by a string. When the freight car begins to move, the string makes an angle 35 degrees with the vertical. Okay, yeah, that is the angle we want. So okay, so there's the tension in the string. This component of the tension is balancing the weight, and this component of the tension is what is giving you the acceleration. Okay. So T cosine theta minus mg equal to 0. So T cosine theta is the y component, minus mg equal to 0. So T cosine theta equal to mg. And then T sine theta is the x component. T sine theta equal to mass times acceleration. Yeah. So if you divide this equation by that equation, then you get tan theta. All right, I'll do this. Okay. So you get tan theta equal to A over G. Okay. And as we mentioned, A is G times tan theta. For theta equal to 90 degrees, theta tending to 90 degrees, this goes to infinity, A goes to infinity. Okay. Yep.
So we're setting those equal to each other because we know that mg has to equal ma.
Mg is not equal to Ma.
So then how?
Oh, all I did was divide this equation by that equation.
Oh, why though?
Oh, I wanted a relationship between A and theta. I didn't want any of these guys anywhere around, so I canceled them. Okay. So this expression is independent of the mass.
Sure.
Okay, so you can hang anything you want there. Okay. So the acceleration of the vehicle depends only on the angle theta. Any questions on that? You guys understand? So just a stuff, object hanging from the ceiling is an accelerometer. Yeah?
And so we wanna cancel out T because we don't know it?
We don't care to know about it. It's not. In this problem, all we were interested, what we are showing to you is that the acceleration of the car is related to this angle.
Okay.
The tension really depends on how heavy this object is.
Sure.
And what we are showing also is that this angle doesn't depend on how heavy this object is hanging. And since it was not dependent on the mass of the object, it's not dependent on the tension either.
Sure.
Yep.
Okay, so it's just because we, right, okay, yes, it's because we want to find directly relationship to theta now, okay.
Did you have a question?
Yeah, don't we solve for the acceleration, or we have to put it there, or like don't we, multiply G both sides?
Oh, well, yeah, okay. So you can put tan 35 and calculate the acceleration.
Oh, okay.
Yeah. All right, so A is tan theta G. So in this case, it was tan 35 G. So it's 0.7 G. That's an expensive car. What number tells you that's an expensive car? This number tells you. Okay. So if you come in my car, all you'll get is maybe about 10 degrees.
So why are you leaving it as G instead of like multiplied by 9.8?
So this tells you this is the force, the thrust is 70% the weight of the car. Yeah. All right. A roller coaster car starts from rest at the top of a track, 30 meters long. 30 meters is roughly from there to that end. Okay, so starts from rest at the top of a track, 30 meters long, and inclined at 20 degrees, and that would be inclined at 20 degrees, to the horizontal. Assume that friction can be ignored. What is the acceleration of the car? Okay, so you guys did an experiment so the Monday folks did this experiment. And we want to find the acceleration. You guys remember the acceleration down an incline is A is G sine theta. Okay. So this is G sine 20 degrees. And then they ask you how much time elapses before it reaches the bottom of the track. So it's how long does it take to get there. All right, so our x-axis will be drawn in that direction, and x minus x naught equal to v naught t plus 1/2 at squared. So here's an expression that involves t, and you can solve for it. Initial velocity was 0, so that term is 0. Okay. And this term is 30 meters. This position minus that is 30 meters. So this is 30 equal to 1/2. A is 0.34 g times t squared. So t is 2 times 30. Okay. So So what we found was if you get the track that we use in lab, cart, and let it slide down this incline, it would take 4.5 seconds, 4.25 seconds. Okay. All right, so this is an Atwood's machine. The device shown is an Atwood's machine, assuming that the masses on the string, masses of the string and the frictionless pulley are negligible. So this is massless, and it's frictionless. Find an equation for the acceleration of the two blocks. Okay. So let's say M2 is greater than M1, and so the magnitude of the accelerations will be like that. The magnitude of the accelerations will be the same. And okay, so when this is massless and frictionless, what does that mean? What are they trying to tell you? I'm sorry? The tension in the cable is the same. The magnitude of the tension. If this was a massive pulley, then the tensions would be different. It would have to be T1 and T2. All right, so this is M2G, M1G. So now what we'll do is we'll write down Newton's second law for this guy. M2G minus T equal to M2 times A. And then we'll write down Newton's second law. We'll write down an equation for this guy. Okay. So M2G minus tension equal to M2 times A. And then tension minus M1G equal to M1 times A. All right, notice what I've done is, for this guy, I chose this direction as positive. M2G minus T was equal to M2 times A. And for this guy, I chose that as the positive direction. T minus mg equal to m1 times A. Okay. And now, you see, if you notice, if you add these two equations, the t's will cancel. So m2 minus m1g equal to m1 plus m2a. All right, so what does this equation look like? See, this is this force, that's the difference in the weight of the two guys. And that's equal to the acceleration of the combined object. So the force, net force acting on it is the difference in the weight, and the mass of the system is the combined masses. So for instance, if the two masses were equal, there's no force acting on the system, and it wouldn't accelerate. All right. So A is M2 minus M1. So again, this is a device where you can tune the acceleration. So let's see what I mean by that. So if M1 were 0, if M1 were 0, this would be 0. M2 by M2 is 1, the acceleration would be g. And that makes sense. If this guy was not there, this would just free fall. The acceleration would be g. If M2 were equal to M1, this would be 0, A would be 0. And then you can think of it this way. What if M2 were 0? Then it would fall in this direction. And if M2 were 0, then A would be minus G. Well, so if you're choosing this direction as positive, it would be minus G. Well, all right, so, I mean, that's just an artifact of the, okay. So you can tune this to anywhere from 0 to G. Okay. And then you can put in the numbers and calculate, but I'll let you guys do that. All right, so this is sort of a similar problem. Again, so let's do this. So a 2 kg block and a 4 kg block are connected by a light string as shown. The incline is at an angle 40 degrees. Friction is negligible. What is the acceleration of the block and the tension in the string? Okay. So again, they don't explicitly state that, but we'll assume that the pulley is massless and frictionless. And we have to assume that because they haven't given us the mass, so you couldn't solve it otherwise. Yeah. We'll call this M2. Yeah. And this is M1G. And you guys remember this would be M1G sine theta. Okay. The component of this weight is, in this direction is M1G sine theta. Okay. So, okay, we'll write Newton's second law for this guy. For this guy, M2G minus tension is M2 times A. And for this guy, tension minus M1G sine theta equal to M1 times A. Okay. Tension minus M1G sine theta is M1 times A. And again, we'll do the same thing. We'll add these two equations. The tension will cancel. So M2 minus M1 sine theta G equal to M1, M2 plus M1 A. So A is M2 minus M1 sine theta Okay, so here's the expression for the acceleration of this block up the incline and the acceleration of this guy. Okay, this problem looks very different than this guy, right? But you see, this guy is really just a special case of this guy. How could you turn this guy into that guy? Can you tell me? Do you see that?
Wrong page.
So, when we're saying that the weight of mass two minus that tension, what are we saying is M2A?
Well, if this guy is accelerating up at A, this guy is accelerating down at A.
Sure. Okay, so the A is in.
And so if this guy wasn't there, A would be equal to G.
Right.
That would free fall.
Why are we subtracting off T though?
We are choosing, well, if this guy's accelerating that way, this guy's accelerating this way, we're choosing this direction as positive, and M2G is positive, and T is, that force is negative. I mean,
That doesn't really answer that question.
all right, so ask your question again.
Why,
We're talking about this.
I don't understand the concept of why the tension is, I don't understand why we're subtracting off T at all.
This is the equation you don't understand?
Yeah.
Okay. So for this equation, okay, I'll draw this object. So there is M2. There's my y-axis, x-axis. There's M2G. There's the tension. Okay, so the tension force, and you'll see why I didn't want to do all of this. And M2G, or we'll say weight 2 is 0I plus M2 GJ. And let's write down the y component Fx. Okay, and this would be the net force. This is the y component of the forces, M2G minus T. So that's the y component of the force, M2G minus T. And that's equal to mass times the y component of the acceleration. And y component of the acceleration is that. Yep, so that. All right, so think of this as one-dimensional problem. That's an easier way to look at it. This is the positive direction, okay? And so forces pointing in that direction are positive, plus M2G, and forces pointing in that direction are minus T,
Okay, sure.
okay?
So now we're saying that's, okay, sure.
And for this guy, that's the positive direction, and that would be T, and this would be minus M1 G sine theta.
Okay, so M2A would be, or, okay, M1A would be M1G sine theta.
Mm-hmm.
Okay.
All right, so now the question is, see this problem, how do you convert this guy into that guy? And if you notice, if you realize, if you made this angle 90 degrees, then this problem turns into that problem. Let's make sure that is true. If you turn that into 90 degrees, this becomes 1. And for the acceleration, you get M2 minus M1 plus M2 plus M1G, which is that expression. Okay? So this fella is really a special case of this fellow. All right. So And you guys understand that for small enough angles, this will always go down. It will accelerate upwards. But if you make this angle large enough and if the masses are such that, see, if this becomes larger than that, then this will accelerate downward. Okay? So you can calculate that as well. All right, so you can put in all the masses, calculate the acceleration, and then put that back in there and calculate the tension. So that's part B of the problem. Okay. So this problem says a contestant in a Winter Olympic event pushes a 45 kg block of ice across a frozen lake as shown below. Calculate the minimum force he must exert to get the block moving. So he's exerting a force like that. The vertical component just pushes the block down. It doesn't move the block. It makes friction greater. The x component of the force, so what is pushing in the horizontal direction is F cosine 25. And when do you get the block moving? Okay, so this is the maximum static friction force. When F cosine 25 minus F, the maximum static friction force, equal to 0, that's when the block will start moving. Okay, so F cosine 25 has to equal the maximum static friction force. What is the maximum static friction force? Is mu s times the normal force. And in this case, what is the normal force? There is mg and there is F sine theta, sine 25. I'll call it sine theta. Okay. So the normal force is balancing those two. So the normal force has to equal this plus this. The normal force has to equal this plus this. Okay. I'll write this as cosine theta. All right, so F cosine theta equal to mu s times mg plus F sine theta. All right, so what we want to solve for is F cosine theta minus mu s sine theta equal to mu s times mg. So F is mu s times mg Okay, so that is the force you need. That's the minimum force you need to get the object started. Okay. Now, when you do a multi-step calculation, you gotta figure out, you got to learn a way to see if your calculations are right. Okay, and so here is a simple way to test it out. Okay, what if he was exerting a force horizontally? Then all you would have to have is F should equal the maximum static friction force. Okay, so if cosine theta were, if theta were 0, this would be 1, this term would be 0, and the force you need would be just mu s times mg, which makes sense. All right, so at least it has the right limit in the limit theta equal to 0. Okay. What if he was pushing straight down, if theta were 90 degrees? It wouldn't move. Okay. So if theta were 90 degrees, this would be, this would be 0, this would be 1, minus mg. Then this doesn't make sense in that case. So anyway,
The friction then stops mattering.
what's that?
The friction stops mattering. You're not pushing the wall.
Yeah. So, we equated this, if it was vertically down, there was nothing to equate to this friction force, so this equation would not be true. All right, so anyway, it had the right limit for theta equal to 0. All right, so once you get this thing started, what is the acceleration once it starts to move? So you can put all those numbers in and calculate that force. And once you get it started, you're applying the same force. Now what happens? This static friction force gets replaced by a kinetic friction force, which is smaller. Okay? And so this guy will accelerate. Okay? So let's do that part B. And now the friction force is mu k times the normal force. Okay, so F cosine theta minus mu k times the normal force equal to mass times acceleration. And the normal force is the same. This is the normal force. So what you would do is, in this part, solve for F. You have to look up mu s for ice on ice, and you have to look up mu k for ice on ice. Okay. All right, let me look it up. All right, you guys will have to look it up, I guess. So look up mu s, calculate that, then you would put that in here and calculate this. Okay. right, before we do this, let me remind you. So let's say you're going in a circular orbit at constant speed. Are you accelerating?
Yes.
Why are you accelerating?
Changing direction.
Yeah, the velocity is changing direction, and at every instant, the acceleration is pointing toward the center of the circle, and it's called centripetal acceleration, v squared by r. And then, so there must be a force acting on it, giving you the acceleration. So here's a roller coaster ride. So at this point, well, so you're going in a circular orbit. If you're going at this at a certain speed, okay, so at certain speed v, your centripetal acceleration is v squared by r. Okay, so there must be you have to have some source of force that's providing you that acceleration. Well, gravity is pulling you down. What if this acceleration is greater than gravity? Then what? Then this track has to push you down to provide the additional force. What if the centripetal force is smaller than the acceleration due to gravity? Then if you're not wearing seat belts, you'll just fall down. You know, your radius of your orbit will become smaller. Your centripetal acceleration, your orbit will be such that this becomes equal to g. So if you're going too slow, then you just fall down. Okay, or you just go on a trajectory that has a smaller radius. So you would wear a seat belt would provide a force, the additional force in the downward direction. Okay. All right. So a child of mass m. We'll just do this problem for that case. This is just making it slightly more complicated, and we're not interested in that. Okay, so a child of mass 40 kgs is in a roller coaster car that travels in a loop of radius 7 meters. 7 meters. So the loop is as big as this room, as wide as this room. Okay, so imagine this room standing up on its end. At point A, the speed is 10 meters per second. We won't worry about point B. What is the force of the car seat on the child at point A? At point A. So okay, so at point A, the centripetal force you need is v squared by r. And so v is 10 meters per second square. 10 meters per second square, and the radius of the loop is 7 meters. Okay, so this is so you see at the top the acceleration is, the centripetal acceleration is 1.4 g's. What does gravity provide you? G. And so the seat belt has to push you down with a force of 4.4 g. Okay. So the seat belt has to provide you that additional force. Okay. All right, so all right, let's So here's what you do when you're designing roller coaster rides. Okay. So all you have to do is you got to make sure. All right, let's actually let me do the rest of the problem. So that was that. Now let's do part C. What is the minimum speed? What minimum speed is required to keep the child in his seat at point A? Okay, so what is the minimum speed? The minimum speed should be such that the centripetal force is equal to G. Because if it's less than that, then the child will come off the track like that, like we said. Okay? So let's calculate the minimum speed. The minimum speed is such that the centripetal acceleration is equal to G. Okay, so in this case, G was 9.8 meters per second square, and R was 7 meters. So okay, so if the car is going at 8.3 meters per second, your trajectory will follow the track. If your speed is smaller than that, then radius will have to decrease because G doesn't go anywhere. So then you would go on a track like this, on a trajectory like that, and you would fall off. Okay. So you see, this was the minimal speed for this track. So here's what goes into designing these guys. You know, all you do is you make sure that the cart starts off high enough such that at this point it's going faster than 8.4 meters per second. And you don't have to wear seat belts and you won't fall off. Okay? All right. This says calculate the velocity of a spherical raindrop. The velocity of spherical raindrop would achieve falling from 5 kilometers. So that's that's the size of that's the height of a thundercloud. In the absence of air drag, and then with air drag present. Okay. So if there was no air drag,
I don't think we can see what you're writing. But we can see the page, just not what you're writing.
okay. Can you see it now?
Yeah.
Mhm.
It's writing stuff you wrote earlier. I think it's replaying something. Like, you wanna look at what it's doing? It's writing out everything you did today.
So it's delayed reaction?
No, it's not, it's playing everything you have written.
Oh, wow.
Did you hit a replay button? Like, I don't even know. That's thing.
So has this been,
No, it just started happening the moment you went on to number 84.
Yeah, we saw this problem, the raindrop problem, we didn't see.
Yeah, we were on 84 and then I just did this.
okay, I don't see a replay button or anything.
Is it doing it on your?
No?
Oh.
Really? That's fun.
Maybe we want to finish this in a maybe it just really wants us to review this document and make sure we have it.
We saw it all live while you were writing it too.
So like we saw this and then it just stopped. And we never saw this.
All right. That's all I've written. So let's see, maybe now. Okay, it's delaying. Well, I'm recording this thing. I don't want to interrupt. Okay, it's gone back real time. Okay, so this problem says calculate the velocity of a raindrop that falls 5 kilometers. Okay, with in the absence of air drag. Okay, so you'll see that. So in this problem, we'll assume this is the x direction. The acceleration, of course, is g. Okay, so the velocity is, so you will use this formula, v square equal to v naught square plus 2ax minus x naught. So there's the final position. Of course, the raindrop starts from rest. So v square is, v is square root of 2 times g times the distance traveled is 5 kilometers, 5,000 meters. Okay, and so you put that in there. Okay, that's 700 miles per hour. You wouldn't be walking in that rate. Okay. So in this case, drag forces are a good thing. So now let's calculate the speed when there are drag forces present. So what happens? The raindrop falls, it starts speeding up, and the drag force increases. The drag force, you guys remember, is proportional to the speed, 1/2 c rho a v square. Anyway, so as it's speeding up, the drag forces increases. Eventually, it equals the weight of the raindrop, and it reaches terminal velocity. Okay. So for part B, we'll calculate the terminal velocity of the raindrop. And so here's the formula for the terminal velocity, 2mgc Okay, so mg is the weight of the raindrop, a is the area of cross section, which is a circular cross section, c is the drag coefficient, and we'll just have to assume a number for that. We'll assume 1/2 for that, and rho is the density of the fluid in which you're falling, and you're falling in air. Okay. Now, of course, the density of air up there is much smaller than here on ground level, but we'll assume the density is constant. Okay. So what we are saying is actually the terminal velocity in the upper part of its journey is higher than here. It slows down. So for instance, if you were skydiving, and this thing started at this rain started and you were at 3 kilometers, the rain would hit you harder than when you were at ground level. Okay. All right. So there is the terminal velocity. Okay, this is air, density of air. So 2 times so actually let me calculate the mass of the raindrop. The mass of the raindrop is density of water times the volume. Okay. So 4 millimeters. The size of the raindrop is 4 millimeters. Take the size across the drop to be that. So radius is 2 millimeters. So the mass of the raindrop, the density of water is 1,000 kg per meter cube. 4 pi by 3. 2 millimeters is the radius. Millimeter is 10 to the minus 3 meters cubed. Okay. So this is whoa. Okay, so this is minus 9, 8. So 8 for the 30, 32 pi over 3, 10 to the minus 6 kgs. What? Yeah, okay, that makes sense. 2 millimeters, so this is a tiny drop. Okay, so that's the mass of the raindrop. 10 to the minus 3 kgs is a gram, so this is about that many milligrams. The mass of this thing is in milligrams, okay? All right, so let's calculate. So now we'll put that in here. So the terminal velocity is 2 mg c density of air and area of cross section. So this is 2 mass is 32 pi by 3 into 10 minus 6 kgs. G is 9.8 meters per second square. C will take that to be half. Density of air at ground level is about 1.3 kgs per meter cube. At 5 kilometers, it's about half of that, but we're not going to worry about all of that. Pi r square is the area of cross section of the drop, and the radius was 2 millimeters square. All right, so this is a mess, but we'll figure it out. Okay, so that's 10 minus 6. That cancels with 10 minus 6. Okay. So So what we get is square root of 64 pi into 9.8 divided by 1.53. 3 times that is 1.5 into 1.3 into pi into 8, okay, square root of that. And this is the velocity, will work out in meters per second. Okay. So 8 pi cancels. All right. This is about 14 miles per hour. Okay, and you can walk in this range.